Good morning, everyone. It is a great pleasure to welcome you all to the Global Water Futures Core Modeling webinar series. My name is Praveen Rokaya. I am the science coordinator of the Core Modeling and Forecasting team, and I want to thank you all for joining us today, despite many online meetings and webinars that we are having these days. So we really appreciate your engagement. Today we have Professor Roy Brower from the University of Waterloo, who will be presenting on advances in hydroeconomics. It would be about 45 minutes of presentation, followed by 15 minutes of question and answer session. Before we begin, I wanted to share that next month on 4th of March, we will be having Professor Philip von Kapellen from the University of Waterloo, who will be presenting on advances in water quality modeling. So please stay tuned. Today, I'm very pleased to introduce Professor Roy Brower. Roy is the faculty lead of the hydroeconomics team. This team is working to develop a new generation of integrated hydroeconomic models for Canada, which I believe Roy will be highlighting today. Roy, we are very happy and grateful to have you here today, and the floor is yours.
Thank you, Praveen. I'm going to share my screen with you, and then I'll get going. Can you see it?
Yes.
Perfect. Yeah, it's in full presentation mode now, I think. Okay, so thank you very much for the invitation. I'm going to talk in the next 45 minutes about advances in hydroeconomic modeling within the project Global Water Futures. And the work that I'm going to present is in collaboration with George Garcia Hernandez, who is the core modeler PDF in Global Water Futures in this particular area. This is the outline of my presentation. I'll give you a little bit of background information, then I'll talk about the general methodological framework, and then I'll give you two examples of how we applied this hydroeconomic modeling framework to the Great Lakes Basin, and then I'll finish off the presentation with discussing a few next steps that we have in the planning for the year and years to come. Starting with the background, so what you can observe globally, I think, starting perhaps in Europe with the introduction of the Water Framework Directive in the year 2000 already, is that policymaker demand for information that tells them what the broader economic implications are of water policy interventions or the impacts of climate change, that demand by policymakers has increased significantly over the past decades. It allows them to make trade-offs, investing in water infrastructure, for example. Water quality improvements has the feature that a lot of these investment costs are directly visible on the budget sheets of the authorities responsible for the water body. Often we are struggling a little bit more with identifying what exactly are the social benefits of all these water policies and water management activities. And then if you look at the existing literature and the various models that are available to help and assist in making decisions in water resources management, they can typically be classified, a majority of them can typically be classified as so-called engineering-based hydroeconomic models. They contain a lot of hydrological detail, but they have typically very little to go on in broader economic terms. They are including often simplified dose-response relationships, and a link with economics is made by simply adding on some economic prices, multiplying them with the impact of increasing irrigation water, for example, how that affects crop yields, and then multiplying the increase in yields with the average price of the crops. So these models that are there are currently specifically focused on sectors. They're so-called partial equilibrium models in economic terms. They don't account for the various interrelationships that exist in economic systems. And that is what we are particularly interested in Global Water Futures. We're interested in identifying more broadly what are the impacts of water policy interventions on the economy as a whole. And that is very relevant if it comes to climate change and larger investment decisions in water infrastructure with large-scale implications. We did a survey already early on in Global Water Futures, looking at all the available hydroeconomic models in Canada. We interviewed the developers, the users of these models, and we identified the types of models that are out there and for what sectors they are used more specifically. So the big question we are trying to identify or to answer in Global Water Futures is how can we improve the integrated economic impact assessments of water policy interventions. And to this end, what we're working on in Global Water Futures is a consistent economic water data and model framework. And we want to do that at the relevant policy level. So typically economic data are available at administrative levels for the province as a whole or for the country as a whole, but decision making is done within the boundaries, the hydrological boundaries of river basins. So we're interested in how these skills can be better matched. And what we are specifically focusing on is the economy as a whole. So that would allow us to assess the broader direct and indirect economic impacts of water policy interventions. So that is what I'm going to talk about. What have we done in Global Water Futures so far, and where are we now? What are the innovations that we brought to the table over the past years and that we're currently working on? This is a picture that I've been using for a long time. The reference is given here at the bottom. For those of you who are not familiar with this picture, this is the Roman god Janus. He's the name giver of the month January, the beginning of the new year. And Janus was able to look backwards and forwards. And I'm using this to illustrate the need for developing integrated water economic accounting frameworks in order to be able to validate and calibrate the integrated models that we're developing. You can develop nice theoretical models. If you want them to work in practice, you need to have the underlying data to operationalize these models. So what we've been doing is investing at the same time in the development of these integrated accounting frameworks as we developed these hydroeconomic models. You need to understand relationships between water use and the economic system in the past to be able to make predictions of what will be the implications of changing your water policy or your water management into the future. That's a little bit the idea behind this picture. In one of the Global Water Futures projects led by Saman Razavi from the University of Saskatchewan, the Integrated Modeling Program for Canada, we're looking at the development of these hydroeconomic models in the Saskatchewan River Basin, and here in Waterloo, I'm working with George on the development of similar models for the Great Lakes Basin. And this is our vision. This is what we're trying to achieve. We're developing multi-regional, multi-sector input-output models that allow us to assess these direct and indirect economic impacts of future water supply disruptions, for example, under climate change. And we want to do that in a way that allows us to compare these models based on a common database taken from the system of national accounts. So if it comes to economic data, the place to look for data that allows us to describe economic activities at a larger scale, the system of national accounts is the place to go. It's the accounting system that produces every year the GDP numbers, or they do it on a monthly basis already. So GDP, gross domestic product, is an indicator of economic growth for a country as a whole or for a province, for Ontario, for example, and it's based on a very coherent, consistent system of accounting for economic transactions between different sectors. It was developed in the 1960s already by the United Nations, and it's used worldwide. And so we're interested in using the same consistent macroeconomic database to develop these macroeconomic models that include water. This is a very simple representation of the relationship between the economy and the water system. We use water as a source and as a sink. We use water to produce all kinds of goods and services, take irrigation water. Once water has been used in different kinds of, especially industrial activities or by households, it transforms in wastewater, and we discharge after treating it or not. The wastewater, we discharge it back into our water system, and then we use it again as a source. And so what we've been working on is identifying where can we find data and information about the economic flows. Those are data provided by Statistics Canada. It's the time period here over which we have data available for making these input-output tables, and I'll talk a little bit more about that in a second. There's a lot of data and information available on water characteristics. So we used data from Statistics Canada as well, different surveys that they conduct over different time periods for different sectors. And we are looking at data that relate to the pressure that economic activities exert on the water system, especially pollutants. And we have two different reporting systems from Environment Climate Change Canada, with which we have been working, including the National Pollutant Release Inventory. And so we're trying to combine in a smart way these different data and information systems. We're not doing any additional data collection. We're just using what is there, but we're using it and combining it in a way that it hasn't been used and combined before. So this is an overview of Ontario, and the red and the blue dots give you information about where exactly we know which kind of pollutants are discharged in the Great Lakes Basin. The red ones refer to the NPRI that I referred to just now, and WSER is another information system from Environment Climate Change Canada that give us information about discharged volumes and the pollution levels of these discharges. And WWTP are the wastewater treatment plants. We also have information about more diffuse non-point sources, agriculture, for example, and how much phosphorus is emitted from different places in the Great Lakes Basin into the Great Lakes. And you see that the darker blue, that those are the higher levels of pollution, are especially found along Lake Erie. We know that we have eutrophication issues in Lake Erie, and that is shown very clearly here in this particular graph. We use the lowest spatial resolution to allocate available water statistics to the river basins, and that is the census subdivisions. And there are around 600 of those in Canada. And that's also what we're trying to do with the economic data. So by putting this integrated accounting framework together, we are able to assess how much of GDP is generated in these different subbasins. And we do that by linking economic activities to these census subdivisions, these around 600 census subdivisions in Ontario, and then we allocate these census subdivisions to the different lake basins. So total GDP in Ontario in 2016 was over 740 billion Canadian dollars. Most of it was generated in Lake Ontario, followed by Lake Erie. It gives us insight in water use in millions of cubic meters, for example, of different economic activities, again, in different lakes and in the rest of the province. And it gives us information about the sources of pollution. So what is the phosphorus emission intensity of different economic activities in the different lake districts that we look at? So this is the total phosphorus emission associated with the value added generated by these economic activities. So this is already giving us a nice idea of where most of the water pressure takes place in the Great Lakes Basin. So then moving from the past, because these accounting systems look at economic transactions and how much pressure these economic activities imposed or exerted on the water system in a year in the past, we use that data to put our hydroeconomic models together, so-called environmentally extended input-output models. They describe the economy in a particular year. It's based on the system of national accounts, as I mentioned. Everything is measured in monetary terms, and we extend these tables with physical entities, variables. So input variables like water intake and the emission of wastewater, for example. That's all measured in physical units. This is how an input-output table looks like. What we have here in rows, I hope you can see my cursor here, is what is produced and what goes out. So you have industrial activities, 1 to n. They produce output that they also use in industry. The rest goes to households for final demand, and that then gives us total output of these different industrial activities. The columns reflect what has to go in order to produce the output. So we have industrial inputs that we need to produce the final demand, but we also import, for example. We need labor, capital, and that's measured through value added. That goes all the way up into these industrial activities to generate our output. So we have total input that has to equal total output, and all that is measured in monetary terms. What we then add is here highlighted in green is how much water we need to generate that output per economic activity. It's measured in physical units, and we have then the so-called bags that are generated besides the goods and services that come out of our economy every year. And we can translate these input-output flows in a linear input-output model, where simply the amount of supply has to equal the total output, and that consists of the intermediate and final demand. So this is the intermediate demand, and this is the final demand. And that is the linear relationship that then allows us to assess if something happens on the supply side. So say there will be less water available, how does that then affect intermediate and final demand, knowing how these different industries are interconnected here under Z. There are some challenges with these input-output tables. As I mentioned already, they follow administrative, not hydrological boundaries. So we have to somehow allocate the economic activities to these hydrological units. Rarely is it the case that available water use data is directly available at the relevant spatial scale for which we want to use it in our models. There is a mismatch often between the sectors as they are identified in the water use tables and in the emission databases of Environment and Climate Change Canada. So some translations, conversions have to be made to make these sectors comparable. And very importantly, if we are interested in breaking down existing provincial or national data about economic transactions, that includes transactions, imports and exports between provinces, for example. So the moment we start translating and disaggregating economic activities at the level of basins, we also have to properly account for the trade that takes place between these basins. So that's an additional challenge. And finally, as I mentioned, the input-output model is a linear model. So we know from experience and from the empirics that there are often non-linear responses, economic responses to external shocks. So the challenge is, how do we account for that? So we regionalize these input-output models, these provincial input-output models. It was done in Saskatchewan. It was done here in Ontario for the Great Lakes. And we do that by making use of census data that are available at the level of these census subdivisions. In Ontario, almost 600 of them. We look at the supply of goods and services, and we look at how many jobs are associated per sector at the level of every census subdivision to produce that output. And there is demand that is measured by looking at the population in every census subdivision. And then the challenge of estimating these intra-regional trades are estimated in the models that we have here in the Great Lakes Basin. They're estimated based on on a combination of two approaches, the so-called flex location coefficient and the gravity model that we estimate. I don't have time to explain all the details of that, but basically what we do is we decompose existing provincial data by looking at how much output from Lake Superior, Lake Huron, Lake Erie, Lake Ontario is supplied within Lake Superior, goes to Lake Huron, goes to Lake Erie, Lake Ontario, but also to the rest of the province, the rest of the country, and even the rest of the world. And so what you can see from a table like this is that if you look at Ontario, it's the largest output, it produces the largest output here with 962 billion Canadian dollars. It supplies goods and services to Lake Superior, to Lake Huron, to Lake Erie, and it consumes a lot inside the Lake Ontario sub-basin as well. But a substantial share of the total output is also exported to the rest of the world. And so what this table illustrates is the relevance and the importance of accounting for these broader economic interactions that exist within the Great Lakes Basin, but also outside of the Great Lakes Basin. So whatever you do in the Great Lakes Basin doesn't stay in the Great Lakes Basin. It has implications for trade flows with the rest of the province, the rest of the country, and the rest of the world. And so that's why we're interested in assessing if you do something with the Great Lakes, you're worried or concerned about the water quality levels, for example. We know that the vested economic interests are tremendous. And so if you affect or you intervene in some of these economic activities, not only these economic activities that you target will be affected, but also associated economic activities, because these sectors do not operate in isolation. And that is exactly what we're able to capture with the models that we are developing. More mathematically, we can represent our model like this. So we have a water-restricted multi-regional input-output model where our objective function is to minimize the impact, whatever the policy intervention is, on the economy. And we have a nonlinear quadratic objective function here where we try to minimize the difference between the baseline level of output or GDP and the reduction in output as a result of the water use restriction, for example, that we're imposing. So we want that difference to be as small as possible. We want the economic losses, the economic costs as a result of a water policy intervention to be minimal. That is what we're trying to achieve. In economic terms, you could refer to this as a sort of a cost effectiveness analysis. And we use a quadratic term here because we want to account for nonlinearities, but we also in that way punish the reduction of low value generating activities, which are an easy target maybe perhaps to reduce the use of water, for example, by imposing a higher penalty as you reduce more of the output in one particular economic activity. That is what the quadratic cost function here represents. We have a lambda here included in the middle, which then includes the sector-specific value added, for example, or activities level, output levels, but we can also substitute that with, for example, employment. So if we're interested in also minimizing, for example, the impact of a water policy intervention on employment, we can do that by including the relevant information in that lambda. So then here we have the constraints. The first one refers to the fact that gross output has to be equal to or smaller than intermediate output final demand. And we have a exogenous final demand here as well, and exports. So everything that you produce is being used either within the industry itself, or it's going to final demand, or it's being exported outside of the relevant area. What is interesting here is highlighted here in red. We have a endogenous and an exogenous component in our constraint, and the advantage of having this exogenous constraint here, which is not dependent on the change on this of this economic activity or output here, X, is that it allows us, as indicated here in the second constraint, to account for minimum supply levels of goods and services. So it allows us, in other words, to account for food security or energy security. So if we want to maintain certain levels of supply of goods and services like energy, electricity, or food through agriculture, we are allowed to do that by including this exogenous term here in this constraint. This is simply a water balance that you cannot take more out of the water system for your economic production, measured here through X. Omega here is a factor of different economic activities that use water, and the use of water cannot be larger than the total available amount of water. And that total available amount of water that is being consumed in these economic activities has to be smaller than the total available raw water. So the processed water in industry, measured here, or tap water used in households, the sum of that has to be less or equal than the total available raw water. And then the final constraint is simply saying we cannot have negative output. Then the output has to be larger than or equal to 0. And the R's, the superscripts, they refer to the different regions. So these constraints refer to different economic sectoral activities undertaken in different regions. So we make the input-output model and the economic optimization procedure region specific by doing it for every region specifically and summing them. So what are the novelties here? The novelties here are that input-output models have been around for decades. They were developed in the 1960s, so there is nothing really new here. We're making use of available data and information that allow us to relatively easy convert available data and information from the system of national accounts into input-output tables and link them to available data on water use and water discharge. The novelty here is that we include this non-linear economic optimization procedure where we try to minimize the loss to the economy as a whole. We introduce region and sector specific constraints, and we account for interregional, inter-industry trade flows in a novel way by combining a gravity model with the flex coefficient that I just referred to before. And the model allows us to account for minimum supply levels, so the food and energy security that I just referred to. We also have a possibility to impose restrictions on the use of inputs. So typically, if you are constrained in delivering a good or service, it takes a while before you can replace that by other goods, for example, by importing goods and services from somewhere else. We can impose the restriction that we can only use domestically provided inputs, for example. So these are the two applications that I'm going to talk to now. So we have this multi-regional input-output model for the Great Lakes. We applied it first of all to assess what are the economic costs, total economic costs. So that's both the direct and the indirect economic costs of future water use restrictions under climate change. It's a paper that was published already in the journal Economic Systems Research. And then another paper that we did was, besides getting water to flow in our model, we also managed to get information in it about phosphorus emission levels associated with different economic activities. And that's a paper that is currently under review. The first paper got a lot of attention last year. This is myself with George. So we were interviewed by newspapers, by CBC, etc., to look at or to explain what exactly it was that we had been doing and what the implications were of climate change for the Great Lakes Basin. So I'm going to start with the first example, where we, based on expectations about the impacts of future climate change on water availability and a so-called water availability index that you see here, that was developed by Environment Climate Change Canada, how future climate change affects that water availability. And what we noticed is that currently the water availability index is already 4 or higher than 4 in the month of August. So there is already a severe pressure on the Great Lakes Basin in the month of August, and you see that in the picture here on the left-hand side. And this is a picture taken from the climate change scenarios that we took from Environment Climate Change Canada. So here are some of the assumptions related to these climate change scenarios: air temperature increase, surface water temperature increase. And so we looked at the impact of those temperature increases on water availability. And we developed 2 different scenarios where we assumed in the first scenario, scenario A, that we want to reduce the water availability index from 0.4 to 0.2, which basically means that we alleviate the pressure on the water system. And that can be achieved by reducing water intake reduction in the summer period over 3 months, June, July, and August, by 4 to 12%. So if we want to achieve a more normal, a less stressful situation for the Great Lakes Basin in the future, water intake reduction has to be reduced by 4 to 12%. Then we have a scenario B, which is the same as scenario A, but where we impose this extra condition that we want to have food and energy security by imposing the restriction that the output from agriculture and hydropower has to meet current domestic final demand. So we disaggregated the output of around 35 economic activities that are listed here on the left-hand side across the different basins and the rest of the province here. So this is all measured in Canadian dollars, different economic activities and the extent to which they take place in these different lake basins. And then we added to that the water intake data that we got specifically for the Great Lakes. This is highlighted in the light blue. This is what we mean with survey data specifically for the Great Lakes. For all these other economic activities, no provincial or Great Lakes Basin data specifically were available. So we had to rely on averages that we took from national statistics that are published by Statistics Canada. So we coupled those pieces of information in the model, and then we ran these scenarios. Here you see the results. So we have information at the provincial level, and we have information for the different sub-basins for Lake Erie, Lake Huron, Lake Ontario, Lake Superior, and the rest of the province. There are 2 scenarios, as I explained. The blue line gives you the scenario A, where we try to reduce water intake by a certain percentage, and then we are interested, so that's reflected here on the horizontal axis. On the vertical axis here, we are interested in finding out what are the total direct and indirect economic costs of those water intake restrictions. And then we have this blue line, which is scenario A, and the purple line here is scenario B. So the scenario B line, as you can see, drops steeply, straight away almost. And it reflects the fact that you impose additional constraints on water intake, especially to guarantee food and energy security. So it is much more costly if you want to impose those constraints. So intuitively, maybe even that makes sense. If you don't impose these constraints, you have much lower total economic costs. The impact on provincial GDP is much lower. You can see that there is a very small impact of around 0.1% of GDP of Ontario as a whole until around 9%. So we're pretty good actually between 0 and 9%. The impact on provincial GDP is fairly small, 0.1%, but then you can see that there is this kink and then it goes up more rapidly here between 9 and 12% to around 0.5%. Yeah, so you increase or you reduce water intake by 4, 8 or 12%. We do it here on a percentage basis, and you see that there is a less than proportionate impact. This is measured in percentages as well, GDP impact on GDP, and it's still around 0.1% if we reduce by 9%. So keep in mind that I told you before that total GDP in Ontario was 741 billion Canadian dollars in the year 2016. So even though 0.1% of GDP sounds like a very small number, if you multiply that by 741 billion Canadian dollars, it's still a large amount of money. It's 740 million Canadian dollars. Up to all here. And then if you go up to 0.5%, it's 5 times higher than that. A 4% reduction here is resulting in a 0.7% reduction. So 0.7% of 740 billion is 5 billion Canadian dollars. And here in the most extreme case, where we end up with a 3.5% reduction in GDP, that amounts to almost 25 billion Canadian dollars if we reduce the water availability by more than 10%. And as I showed you, we can do this for the province as a whole, and we can do this for the different subbasins, where you see very similar patterns. If you impose this additional constraint of food and energy security, the costs will be much higher. So I already went through this. I'm going to skip this, and I'm going to move to the second example. So as I mentioned, we also got phosphorus to flow in the model. There's a long history of discussion and policy making in the Great Lakes Basin when it comes to the reduction of harmful algal blooms. Eutrophication is a major issue. There have been various plans, agreements. Most recently, there is this Lake Erie Action Plan that aims to reduce phosphorus loads by 40% in the Central Basin compared to the 2008 level. I probably don't have to explain to most of you what goes on in these lakes. This is Lake Erie. You see a lot of blooms going on. That's the green stuff in the lake. This is Lake Ontario. It happens a lot around the edges of Lake Huron, and even if you look carefully here in Lake Superior, we already have some blooms. So we're interested in finding out, if you implement that policy in the Great Lakes Basin, how much is that going to impact the economic system that depends at the same time also on those Great Lakes. First of all, here is a graph of the direct emission levels of different economic activities of total phosphorus in tons per year per lake region. Ontario has the highest level of emission. What we also did was estimate a so-called phosphorus footprint. So what you see here is the emission level of from coming out of different lake regions and where it ends up. So you see here, for example, that Lake Erie has a relatively low amount of emission for goods and services that are produced and consumed in Lake Erie or in and around Lake Erie itself. Most of the output goes to the rest of the world here. So the dark blue represents what comes out of Lake Erie. So a lot of the pollution associated with the total phosphorus emissions into Lake Erie is associated with the production of goods and services that are ultimately exported outside of Canada. So that is what is giving us information about the footprint of the economic activities in the Great Lakes Basin. We run through 4 different scenarios in this particular study. So we start with scenario A, where we assess how the economic costs evolve as we reduce more of the total phosphorus emission. So you see that here on the horizontal axis, a percentage reduction of TP for the whole Great Lakes Basin. How does that affect the GDP in the province? And then a nice thing that we can show you here is that first of all, you can see that as you increase the reduction level of phosphorus the costs go up exponentially. So the first couple of percentage points reductions don't cost that much, relatively speaking, but then it goes up fairly quickly, and then it becomes exponential here as you move towards this 50%. 40% was what was the aim was for Lake Erie only. And then we can identify how much of these costs are direct costs to the different economic activities and how much of these costs are indirect costs. For the Great Lakes Basin, we also are able to identify how much of these indirect costs are related to the rest of the province and how much of these indirect costs are related to trade flows with the rest of the world. And so that's indicated by the different color coding in these bars. So this was imposing a restriction on the whole Great Lakes Basin, and then the model simply looks for the least cost way to reach a 10, 15, 20, 25% emission reduction level for the entire Great Lakes Basin. We don't impose any other restriction. Then in scenario B, what we are saying is look for the least cost way. So what are the lowest costs to achieve the same total phosphorus emission reduction just for Lake Superior, just for Lake Huron, just for Lake Ontario, and just for Lake Erie. And again, in Lake Erie, for example, you see this exponential increase in the cost as you move further to the right-hand side. So we can assess the economic impacts of emission reduction levels or policy targets for the whole Great Lakes Basin, and then we leave it up to the model to identify which economic activities where should be reduced to reach these emission reductions. Here we're looking for solutions by focusing on specific lake basins only. Scenario C is looking for emission reductions in specific sectors. So here we impose the restriction just on agriculture in the Great Lakes Basin. So across all the different lakes, but just in the agricultural sector. So again, we reduce phosphorus reduction by a certain percentage, and we look at the percentage impact that has on GDP in the Great Lakes, GDP in the Great Lakes Basin, but also on the province as a whole. So here's the percentage change in GDP, and here you see the absolute value in Canadian dollars. So we do that for agriculture, for example, and for manufacturing. And then finally, we have scenario D. We look at the same emission reduction by targeting specific sectors in specific lake basins. So agriculture is the largest contributor to TP emission levels in Lake Erie. So if we want to reduce TP emission levels in agriculture in Lake Erie, what are the associated costs? And here we focus on Lake Ontario. It has a different economic structure. It's much more focused on manufacturing. Lake Erie is a typical agricultural lake district. In Lake Ontario, we focus on manufacturing, what has to happen there, and how does that affect the total economic costs. So I've come to the end almost of my talk. Important to conclude from that second study, again, is just like in the first study, is that our pollution abatement costs, they differ. They differ because we have different emission intensities of these different economic activities taking place in different sectors and even in different basins. So that's why we are not facing the same constant marginal cost across activity and basin. That varies for the reason that I just mentioned. And then what we also did is we looked at the Lake Erie Action Plan that I referred to before, and where they aim to reduce TP emission levels by 40%. If we look at the scenarios that we investigated and especially look at the costs of reducing 40% of the total phosphorus emission levels in Lake Erie under scenario B, for example, the total costs are 1.2 billion Canadian dollars. If you look at the literature, the existing literature, and this is a study by a group of people, including scientists from Environment Climate Change Canada, published in 2019, where they looked at the social costs of harmful algal blooms in Lake Erie on the Canadian side specifically. They came up with this particular number of 270 million Canadian dollars per year. So if you compare the costs of reducing pollution levels and what that will achieve, namely these avoided damage costs, the pollution abatement costs are a factor 5 or orders of magnitude higher than the benefits in terms of avoided damage costs. If we just focus on the GDP in Lake Erie under scenario D and focus on agriculture in this particular case, which is the largest emitter of total phosphorus, the costs go down to 0.8, 0.9 billion Canadian dollars per year. But then still that is orders of magnitude higher than the 270 million Canadian dollars that were presented in this study in 2019. So if you look at these graphs that I showed you before, and you look at the break-even point, and you assume that this is the right number for the social environmental damage costs of eutrophication, and you look for this number in terms of pollution costs. If you then look at these abatement cost curves that I showed you before, the break-even point is found between 10 and 15 total phosphorus emission reduction. And I can very quickly, I'm not sure if I have time to do this, but I can very quickly show you that here, for example, this is scenario B, where we want to reduce total phosphorus emission levels across the individual lakes. This is Lake Erie. If you look at the costs increase and you want to reduce phosphorus by 40%, you get that very high value of 1.2 billion that I just showed you. It's around here. If you look at zero, so this is measured in billions of Canadian dollars, this axis, 270 million Canadian dollars is around here where my cursor is. Then you go to the right, then you see that you are somewhere between here 10 and 15% where you will find that break-even point. Okay, that were the conclusions of the second case study. This is my last slide. So I was asked to talk a little bit more about the advancements in hydroeconomic modeling. I'm just summarizing once again what I showed you in the beginning. What we managed to do in Global Water Future is develop this set of models that are consistent in terms of the data, the underlying data and information that they're using from Stats Canada. Those input-output models have been around for a very long time, including input-output models that incorporate water use, for example. What is new here is that we impose this nonlinear economic optimization procedure. Because one of the major critiques of input-output models is that it is a linear model, and we don't expect linear relationships between a reduction in water supply, for example, and the impact that that has on our economy. And what I showed you was exactly that. Our marginal abatement cost curves, they change depending on the size of the water use restriction, the size of the emission reduction. We introduce region and sector-specific constraints. We deal with inter-industry and inter-regional trade flows in a very novel way. I didn't have time to explain that to you, but it is a completely new procedure that we developed, and it's very crucial to the outcome. I haven't shown you here any sensitivity analysis that we did, for example, in the first paper, but we do sensitivity analysis with these trade flows, and it has a high impact. It really impacts the results depending on how you account for these trade flows. We are able to account for food and energy security, for example, and I mentioned this last point already as well. We can impose even more constraints by saying by Canadian instead of by international once a constraint occurs. Next steps. We're very interested in extending the existing multi-regional input-output model to the US side as well. We're looking into that already. There are some additional challenges there. To be honest, it's not going to be a very easy thing to do. There are 8 different states in which different parts of the Great Lakes Basin are found, and but we're trying our best to extend the model to also have the US side there, because that will make a significant improvement. We're working on more advanced models, computer general equilibrium model with built-in drainage basins. So the difference between multi-regional input-output models or input-output models and computer general equilibrium models is that computer general equilibrium models allow us to play around much more with economic policy intervention. So if we want to introduce a water quality trading market, for example, or a water market, water trading market, that is impossible in the input-output model. We have many more features available in our computer general equilibrium model, including playing around with the technical input coefficients as a result of technological innovation in upgrading wastewater treatment plants, for example. These are things that we cannot capture in the input-output model, but that we are hopeful to be able to capture in the general equilibrium model. And then finally, we're working in Global Water Futures also on a new project. It started in September, October last year, where we focus on the quantification in economic terms of improvements in water supply and water quality. And we are also interested in building in these benefits more explicitly, or coupling these benefits more explicitly to our hydroeconomic models. Here are some references. There are some papers already published. The one with George, I already mentioned in economic systems research. The work with Leila Eamon and Saman in ecological economics, the river basin model for the Saskatchewan River. Leila has done some interesting work where she also looks at the temporal stability of these models, and the paper that we've done on nutrient emission reduction policies is currently under review. And that is the end of my presentation. Thank you very much for your attention.
Thank you, Roy. That was a very informative presentation. We'll be now moving towards the question and answer session. I will start with a very generic question that I have. So in many other hydrology field, most often, assessments are done within a physical boundary, like river basins. But in hydroeconomics, I feel like the values and goods, they may frequently transfer across the physical boundaries. So I'm just wondering what kind of challenge this presents in your assessment or calculation.
Yeah, so that's a very good question, because that is indeed one of the major issues. The trade flows are typically represented at the level of these administrative units, so between provinces. So when we are trying to build these hydroeconomic models that fit these hydrological boundaries, we also somehow have to relocate or reallocate these trade flows between the sub-basins instead of these provinces, and that is a really complicated procedure to undertake, because there is no. So we have the provincial data, and that is the reference point, but we basically do not know how trading occurs between different basins. So in the Great Lakes Basin, between Lake Erie, Lake Ontario, Lake Huron, and Lake Superior, for example, we don't have that kind of data, and information is not available anywhere. And so it requires for us to do some additional modeling to get these trade flows correctly, or as accurate as possible as we can, into the model.
We have another question from Lucas van der Bank. So for scenario B, when you broke down the cost for each individual lake related to emission reduction, was each lake look at it as isolation, so no efforts are done in other lakes, or was it assumed that efforts will be executed in each lakes in unison? How do you account for interrelationship between the lakes?
Yeah, very good question. Also, so what we're asking the model to do when we focus on one lake only is solve your problem in your own lake area. So there is no connection indeed with the other lakes. You have to solve it by focusing on the emission levels of the economic activities that take place in your own lake basin. So that is a very strict condition, and often then also results in higher costs, because you don't allow any substitution of reducing economic activities across the different basins. It may be more cost effective to reduce emission levels, for example, in another basin, and focus there first before you start touching the economic activities that take place in a basin where it's much more expensive to reduce economic activities. And that is reflected in the fact that we have these varying marginal abatement costs. Those abatement costs differ per sector, but also per region. And they give us very nice indications where, not only what kind of activity we should target, but also where.
We have another question. It's anonymous. So regarding Lake Erie, your research is saying that it will cost us more to get us to the 40% reduction, around 1.2 billion, than what we would lose, 270 million. Where does that leave us in terms of what we should do now if we want to preserve the lake? It doesn't sound like economic arguments would be that helpful if one wanted to advocate for the change.
Yeah. So this is a very important question. So first of all, the question is how reliable are the numbers? I think there are uncertainties surrounding the modeling results that I showed you. There are also lots of uncertainties surrounding the value estimate that was presented or published in the literature. So we have to be very careful in how we approach this. But in principle, the trade-off is in economic cost-benefit terms is very easy. You have pollution, you have to abate it, you have to reduce it, and then you avoid the damage costs of eutrophication. What I'm hinting at, what we are finding in our outcomes, assuming that these numbers are more or less ballpark, or how do you say this in English, are more or less correct. The pollution abatement costs are much higher than what we would avoid in terms of the economic values associated with all kinds of activities that are damaged as a result of eutrophication. So we would need to look very carefully into what exactly are the economic activities that are included in these avoided damage costs. But it shows that the economic optimum level of pollution may not necessarily be the ecologically most desired level of pollution. We are not accounting in economics for those ecological considerations at all, and they are very important. But if you just look at the economic values involved, then the pollution abatement costs are orders of magnitude higher than these avoided damage costs. And it's absolutely not the only criterion on the basis of which decisions are being made, but we are pointing out that so you come up with this 40% reduction, the costs are going to be significant. And what we're also showing is what I try to point out is that what happens in Lake Erie doesn't stay in Lake Erie. Most of the agricultural production in Lake Erie is exported. So you intervene in the agricultural sector in Lake Erie that has a cost, a price that goes on, that is beyond the agricultural sector just in Lake Erie. Lake Erie's agricultural sector will be impacted, but other associated industries as well.
So we have another question from Heavy. He says, thank you, Roy, for this talk. You mentioned the drawbacks of different scenarios. I wonder if you can suggest a new optimized scenario based on your findings.
I'm not sure if I understand this question. So if I can come up with another scenario.
So you talk about the drawbacks of different scenarios, right? So is there a new optimized scenario based on your findings?
Okay. No. Okay. So I think I understand. No. So no, we didn't identify. So what I'm trying. Well, we didn't identify the best scenario. All I try to illustrate here is how you can use and how useful perhaps it is to use these kind of models that are spatially explicit and give insight in the extent to which the costs are borne inside an area or outside an area, inside a sector or outside a sector, in the economy as a whole. But the person who asked the question has a very good point that in principle, because we have this economic optimization module, we can identify what the least cost way is. The question is how do you want to find it? As an economist, I would say start with scenario A. because then you have the biggest number or the highest degrees of freedom in identifying what sectors should be targeted where to reduce or minimize your loss in GDP. If you start saying, I just want to do it in Lake Erie, you constrain the search procedure, and it may be more costly to just do it in Lake Erie if you could perhaps also find solutions in other areas. A very important point that I have to make here also is that it depends, of course, also on how connected these lakes are, because keep in mind that I'm not addressing that in this particular exercise. All I'm showing you is the emission of total phosphorus in specific lakes, but I am unable to analyze with this model how doing something in one lake might or would affect the ecological status of another lake.
I'm looking at the time here, and we are 1 minute past the hour mark, so I think we'll stop the question and answer session here. Thank you again, Roy. I also want to thank everyone that attended this webinar. Just a reminder again that next month on 4th of March, we'll be having Professor Philip Van Kapellen from the University of Waterloo, who will be presenting on advances in water quality modeling. So please stay tuned. That will be all from my side. Thank you again, everyone. Roy, do you have any last comment?
Oh, thank you very much for the invitation, and if anyone still has some follow-up questions, I'm happy to answer them offline. I cannot see the Q&A, but thank you all for your attendance.
That is all for today. Thank you, everyone.